23. Printing life. Why replacement organs turned out to be harder than ink. The prediction. What we thought. As biology met engineering in the late 1990s, an extraordinary promise emerged. We would print replacement human organs. Using a patient's own cells, scientists would grow hearts, kidneys, livers, custom-built, rejection-free, and available on demand. Organ shortages would vanish. Transplants would become routine. Waiting lists would be relics of the past. In this vision, medicine would move from scarcity to manufacturing. Bodies would be repaired with precision. Deaths caused by organ failure would steadily decline. Standing in 1999, this sounded radical, but not implausible. If cells could be cultured and tissues grown, why not assemble them layer by layer? Why this prediction made sense in 1999. The late 1990s were a moment of deep confidence in biomedical engineering. At the time, tissue engineering was advancing rapidly. Cell culture techniques were improving. 3D printing was emerging as a manufacturing method. The Human Genome Project suggested biology could be understood and therefore built. The logic felt clean. Organs were structures made of cells. If printers could place material precisely, then cells could be arranged the same way. Scale up the process, add blood vessels, and the problem would be solved. This belief fit perfectly with the millennium-era optimism that engineering would conquer biology. Diseases would be cured. Parts would be replaced. The body would become maintainable rather than fragile. For younger readers today, it's important to stress how severe the organ shortage felt in 1999, and still does. Thousands died each year waiting for transplants. The appeal of printing organs wasn't speculative luxury, it was moral urgency. Who said it, and where? The idea gained mainstream credibility through coverage in Scientific American and similar publications in the late 1990s, which reported on early successes in tissue engineering and experimental biofabrication. Articles described growing skin, cartilage, and simple tissues in labs. Researchers spoke cautiously, but headlines carried momentum. If flat tissues were possible, complex organs felt like the next logical step. Unlike some futurist predictions, this one wasn't driven by a single personality. It emerged organically from laboratories, journals, and conferences. The excitement was collective and contagious. By 1999, bioprinting had entered the public imagination as a near-term medical revolution. What actually happened 2000 to 2025? Progress came, but slowly and unevenly. Over the next 2 decades, scientists learned how extraordinarily complex organs truly are. Printing cells was one thing. Printing functional systems with blood vessels, nerves, immune compatibility, and long-term stability was another. By the 2010s and 2020s, simple tissues like skin and cartilage became viable. Mini organs, organoids, were grown for research. Experimental bioprinted structures entered trials. Vascularization remained a major bottleneck. Organs are not static objects. They are living systems that respond, adapt, and self-regulate. Replicating that behavior proved far harder than assembling structure. By 2025, no fully bioprinted, fully functional human organ had entered routine clinical use. But the field had not stalled, it had recalibrated. Bioprinting became a research tool, a testing platform, and a partial solution rather than a full replacement. Progress was real but incremental. Verdict: status, in progress. Organ bioprinting has not fulfilled its original promise, but it is advancing steadily. While fully printable replacement organs remain out of reach, significant progress has been made in tissues, organoids, and hybrid approaches. The destination has not changed. The timeline has. Why it played out this way? The central mistake was underestimating biological integration. Organs are not just shapes. They are ecosystems. They require blood flow, immune tolerance, signaling pathways, and continuous maintenance. Printing structure without function proved insufficient. There were also regulatory and ethical constraints. Testing life-sustaining organs in humans demands extreme caution. Progress slowed not because of lack of ambition, but because failure carried real risk. Unlike software, biology does not tolerate iteration at speed. The future didn't reject bioprinting. It revealed how far the mountain still rises. What this prediction teaches us about the future. This case illustrates a recurring pattern in biotechnology forecasting. Engineering timelines collapse in theory and stretch in practice. Biology resists shortcuts. Each breakthrough exposes deeper layers of complexity. Progress continues, but rarely on the schedule imagined during moments of optimism. In 1999, printing organs felt like a natural extension of printing objects. In 2026, we know the difference between ink and life is not incremental, it's fundamental. The future delivered movement. It did not deliver miracles. One sentence takeaway. We learned how to print living tissue, but discovered that building a living organ is far more than assembling parts.